Hi everyone, my name is Venkata Harish Kajur and my partner is Luchan Mao, and our application project is on connections between El Nino and La Nina and regional abnormal weather. Motivation. Of course, extreme weather is of special interest because of its devastating power. By utilizing parallel computing and the public datasets available to us, we can validate theories which wouldn't be possible without having knowledge in meteorology. We want to match El Nino and La Nina years and known patterns of their effect with regional abnormal weather events and find the regions that are most severely affected by El Nino and La Nina. This is a data-intensive task with limited dependency, and therefore we can fully take advantages of our computing design. Global surface summary of the day data is stored in S3 as CSV files in the Amazon Web Services. Records for each site for each year are stored in independent files. If we're handling records for 5,000 sites in 40 years, the input will be 200,000 files and the performance will be unacceptable. So what we had to do was select the data from the metadata and generate a file list, download the data files, convert them into one or several large big files, and then upload to HDFS. And for the data processing, defining a abnormal weather event for a site is the difference between monthly mean temperature and the 30-year mean value, which exceeds two times the standard deviation. If an abnormal weather event happened in one of the El Nino or La Nina periods, then it is counted as a match for the site. Results are a list of sites ranked by the number of matches, and since input files are structured tables and the analysis is a sequential process, Pig is a good choice for this. Hive will also be able to do the same thing, but with similar complexity, but requires loading the data into database, and so it therefore introduces more overhead. In our cluster setup, we have a master which is using T2 medium of AWS. I mean the T2 medium, the server with 36 GB of storage, and the slaves are using like a T2 medium with 16 GB of storage. And our cluster sizes are tested with 4, 5, and 6 nodes with 5.2 GB and 10.5 GB of input data. And now I'll hand off the presentation to Rochan, who will go over the implementation and evaluation.
So let's look at implementation. So we are using GSOD data, and GSOD stands for Global Service Summary. So it's just some weather measurements like temperature, wind, humidity, pressure. So it's basically located on S3 storage, but as my friend just mentioned, we didn't take that as input directly for performance reason. So what we're doing is use a pig script to generate a list of links to these data files and download them to a local storage and do some concatenation and upload them to HDFS and then do the processing. So basically, for data selection, we're just selecting those sites with more than 35 years of records and a range of keywords as HTTPS links. So we got a list, and we use wget to read the list and download all the files. Then we wrote a C++ program to concatenate all those files into two big files and upload them to HDFS. Then the second part, data processing. So basically, I don't have much to say. It's done with PyXpert again. So it's basically just some SQL style operations, filter, group join, and I use the package to calculate standard deviation. We know that Pig supports some user-defined functions. So basically, the script is just 20 lines of code, and it'll be much simpler than the equivalent MapReduce program. So here are the results. So our program generated a complete list of more than 4,000 sites, ranked by the number of matches, which means how severe are these sites affected by global normal weather. So I just listed these top 10 sites that are most severely affected. So, but actually, I'm not very confident about whether these locations are actually the most severely affected, because we're using a very rough method because we only have limited time for this project, and actually it could work out differently, but this is just a rough idea about which part of the world is most affected by these weather events. So this is an evaluation of scalability and performance. So we can see the running time of the data processing part is of course reversely related to the cluster size. So we can see basically the running time decreases smoothly with increasing cluster size, but for the 10.5 GB input data it decreases more significantly. So if we calculate the inverse of running time and define that as running speed, then we can infer that the data processing part is actually linear scalable. That means the running speed is actually linear related with the number of nodes. So basically, I think this is because our input data is completely has no boundary, so it's completely scalable.